This is a brief video about fundamental modeling assumptions about stock price behavior over time. If you're in Economics 136, you may have heard this lecture live, or you're going to hear it in the future. I have it here because it's a complicated lecture. It's kind of deep in the subject, and some students might want to review it. Also, other students outside the class or alumni might care to see what we're doing in this class, and so this is a key lecture, and it's being archived for that purpose. So your time is valuable. Let's get to this. Now, for purposes of mathematical ease, and because historical data actually does conform to this kind of behavior, since the time of the development of the Black-Scholes differential equation and the Black-Scholes-Merton options pricing model, we assume that prices and their paths and their growth rates are assumed to be continuous, which is a safe assumption even though we know that markets break down over the night. We'll assume that the price behavior of a financial asset is independent of its past behavior. We're assuming that it's a Markov chain, and that also is referred to as assuming that it's a random number walk. Now, this is all very debatable, but is the basis for a lot of modern modeling. And we could also come and debate that assumption and relax it later on if we want to. But for right now, it's very useful to begin with this assumption. This does, in its current state, deny the possibility of technical analysis and charting. So we're going to have to relax this assumption if we're going to do or accept any technical analysis. But for right now, we're going to accept it. This does not mean that the price of a share of stock is unrelated to its price the previous day. In effect, the price of stock on any given day is sort of launched by its close on the previous day. So in the kind of assumption we're making here, there's a trend that may be underway. But you cannot determine the future patterns of stock price behavior based upon patterns that you have seen in the past of that behavior. That's largely what we're assuming here. The assumption implies that we can use historical time series data for financial assets, and especially for stocks, to partly estimate measures of their risk. Now, we know that history doesn't always repeat itself, so these measures of risk are not perfect, but it's a good starting point. And we're going to assume that the rate of return of the financial asset in question can be represented as a random variable, and that indeed its distribution will fit into a normal distribution or a Gaussian distribution. This assumption requires that when working with raw time series data, that it has to be converted to continuous log growth rates to use it. And so that's one of the first things we do in Economics 136 before we begin to make risk estimates. At some point also, we may care to test to see if this distribution in fact is normal by using a test like the Kolmogorov-Smirnov normalcy test or some other. And in the class, of course, we addressed that, although not in this video. Now, essentially what we're saying in terms of its visual representation is that the assumed probability distribution of a financial asset's continuous growth rate, as we'll see later its log growth rate specifically, is Gaussian or normal, and it fits this kind of approximation down there. If you look at the axes, if you're using daily growth rates, which is what we do in Econ 136, then the values down there, like 0.02 or 0.018, are going to conform to those that we estimate actually in the class. Now, to remind ourselves of what the Gaussian distribution is, the top expression shows the probability density function, and the expression right underneath the statement of that is the Excel method for estimating that. The one on the bottom is the probability cumulative distribution function, and the Excel command or formula is shown for that as well. And you've probably seen these before. It's also confirmed in Wikipedia and other statistical sources, and it's easy to map when you're using Python. So you can go and review this if you want, if you're uncomfortable with what a normal distribution means, I should say, but for the time being, I'll kind of assume that you know what it is. We can also easily convert the data once we have it to a standard normal distribution, which will become very convenient for us. And a standard normal distribution, which is normally realized by taking the data we have and normalizing it in some way or the other, is a normal distribution that has a mean of 0 and a standard deviation and variance of 1. Now that's convenient because traditionally it's been very easy to estimate probabilities of being within a certain range in this distribution, or being past a certain point in the distribution, or before a certain point. And that, of course, is what we care to know about in this class. If we are, for example, estimating the values of call options, then we may want to estimate the probability that the stock price will be past the strike price of a now out-of-the-money call option within 4 days. And so making these kinds of assumptions, if they have any validity, makes those kinds of estimates very easy to undertake. We can also sort of apply the 68, 95, 99.7 rule associated with normal distributions, where in the distribution we can say that the likelihood of being within one standard deviation is 68% approximately. The likelihood of being within 2 standard deviations is 95%, and the likelihood of being within 3 standard deviations is 99.7%. And remembering that gives us the ability to kind of eyeball some data to figure out crude probabilities. Now, our pure stock behavior model, based upon this assumption that the log growth rates are normal, is something you may have seen before if you've used a Monte Carlo simulation, or if you've had any exposure to the origins of the Black-Scholes-Merton option pricing model. This is assumed or implied in traditional option pricing models. It's very easy to demonstrate with the Monte Carlo simulation. It does indeed have a lot of empirical weight. This is actually quite a good model. And it's very easy to model with Python, and it's fun to model with Python as well. So we're going to assume, at least initially, that a stock price over time follows geometric Brownian motion, where the log of the stock price follows Brownian motion with drift, as shown there in that differential equation. And so we say, well, this tiny change in the price is going to be equal to the drift times the current price plus the volatility times the price times sort of a random draw from a Gaussian distribution. That's kind of what that epsilon term on the in there means. Now this is easier to understand when we see it used in a Monte Carlo simulation, so let's wait until we see that before we try to figure through what this model is going to say. Right now we'll just accept this simple expression of it. The first term on the left side says that the behavior over time is going to be a function of the drift, and it's going to be influenced by noise. Noise is the expression on the right side. So that differential equation, when it's solved, which has little meaning at the current time, but will begin to mean a lot when we start building options pricing models, is this expression right here, which I'm not going to read out here. You can see it explained on the video. It basically, I guess I will read it out briefly. It's the current price times Euler's number to the power of the growth rate adjusted by half variance and a random draw. And again, if you're kind of uncomfortable with this derivation, take a look at Wikipedia's treatment of geometric Brownian motion and related discussions. This material is derived in the textbooks from what is called Ito's formula. The derivation is very complicated and kind of hard to follow, and most of the financial textbooks, including Hull, don't show how it's done, and so you have to take it as a matter of faith, which I'm asking you to do here. But later on in a lecture, we will actually try to go through the derivation. Right now, you do have to take it as a matter of faith. And the expression on the top therefore implies that if we take the natural log of the price ratio, current price over the initial price, then that expression, the adjusted mean, falls out. And where t is made to equal 1, so we're talking about a one-day volatility measure, then the natural log of the ratio of today over yesterday or tomorrow over today is equal to, once again, the adjusted mean plus a random draw. It's also going to be the case, I'm going to add this now, and you may not understand it, but it will be useful later on. When we talk about the random draw in terms of the component of the price movement that is not the drift, we're sort of assuming that we're playing a game where we have a draw, but it's not a draw that's discrete, it's a draw from a Gaussian distribution. And then we multiply that times our estimate of the standard deviation, which is our risk measure for this, and that contributes to the movement of the price over time. Now, if mu is being drawn from a Gaussian distribution, as we're assuming, then if we convert it back to prices over time, as we'll show here in just a minute, then the expected value of that price in the future is reducible to a very simple expression, which is the price at the current time times Euler's number to the power of our drift modified by time, or multiplied by the time, in our case, of days. So that expected value expression there becomes very important and makes it very easy for us to estimate pricing probabilities, as we'll see later in the course. The variance term there also falls out. Again, we're looking at the results of a log normal distribution. We don't use that specific variance term for anything, but we're showing it here. And the standard deviation of that log normal distribution is going to be the square root of variance. Now, probably at this point, if the live lectures are any measure, you're somewhat confused about what's being said here. So I've arranged a series of diagrams or graphs that I hope explain this a little better or a little more deeply. And this graph I've had around for many, many years to represent how geometric Brownian motion of this Markov process is supposed to work. Now remember, there's two components to the price behavior. One of those is the drift, and the other is noise, which we're calling volatility. Now, the drift itself may be determined by actual economic factors. We argue, for example, in Economics 104 that the performance of a stock is largely determined by a corporation's earnings and earnings report and their growth of revenue and the like. And so we're making the claim here, although we don't state in this model what determines the drift. There is drift, and it can be non-zero drift. It can be positive. And so in this diagram here, we're representing the drift as determined a priori and a green line. And so we start with that little blue dot on the left, and then we roll the Gaussian die. Now, we're going to go up that drift line because that's included in the equation, but we'll drift off the drift line because of noise. That is represented in the second half of the equation, and that results in the second blue dot being somewhere near the drift line, but probably not right on it. In the way this model works, the next day is simply a brand new draw. There's no memory of yesterday except perhaps remembering it to evaluate risk estimates. Nothing that happened yesterday is a function of what the price is going to do today. It's just another roll of the die with no change in circumstances. You draw from a Gaussian roll, and again, you get placement somewhere. And the third dot is drawn, and the fourth dot, and the fifth dot. And so the movement of the price over time, which is going to more or less be positive, is going to be primarily determined by the drift, but is going to be influenced also by the noise. But there is no looking back. If, for example, as you see in mean reversion models, the drift or the result of all of this draw starts to rise above the initial trajectory of the drift line, there's no looking down and realizing that's true and mean reversion back to that drift line. Every single day is simply a new day, and you start from the point that you're at with the new drift noise combination. And that's a fairly useful way to start this. Now still, I suppose for you it's fairly abstract, so let's use an example drawing upon a Monte Carlo simulation. The kind of Monte Carlo simulation that we're using here makes the same assumptions that we made in assuming this is geometric Brownian motion. So in our Monte Carlo simulation, which is discrete, of course, when we apply it, the price at times t is equal to the t plus 1, I should say, the future price, is equal to the price at times t. Now again, in our applications, we'll be using daily data for a while at least, and so we'll be talking about the price tomorrow and the price today. We're not using annual data, and we're not making annual drift estimates or anything. It's all daily. We'll say the price at t plus 1 is equal to the current price times Euler's number to the power of mu minus variance divided by 2 plus the volatility term or the noise term. And so, as we say, this is kind of a gambling game. We have a special die. It has a Gaussian distribution. It has a mean of mu and a standard deviation of sigma. And at step t in our world, we roll the die. We take the result of that roll, make that the power of an exponential, and multiply it times the value of p. And then we do it again and again and again. So when we look at historical time series data, we sort of make the assumption that that has actually happened, and that's what we're witnessing. Again, the epsilon refers to a random selection from a standard normal probability distribution with a mean of 0 and a variance of 1, and that is multiplied times our standard deviation. So when you take a look at a mapping of a Monte Carlo simulation done that way, and this is the mapping that was done in Excel because they're easy to read, you can see a number of mappings here, different colors of course, they all start at the same point, and we're assuming that the stock is trading at 10, and we want to do a 6-month strangle on this stock with call and put options, with a strike price of 10.5 for the call and 9.5 for the put. And I think we're assuming here that we have an alpha, although I don't say that, so it may not be the case. So the stock has to go above or below the strike price for us to make any money, but we also have to cover our option costs. So the red line represents being in the money on the call, the blue line represents being in the money on the put, and the green lines represent being profitable on those given the cost of the option. So as you can see, every time we run a simulation, it produces a random path that's a little bit different from every other time. And that's what's sort of assumed in the Markov chain. Now, if you look at this, it'll look quite a bit like what you expect to see as stock market behavior. It does more or less look like this. It also shows the extent at which it's not really precisely predictable, but we can kind of have a feeling for its likelihood of being within certain ranges. We can see how many times, for example, these options go in the money or become profitable by doing a Monte Carlo simulation. So perhaps this will be useful. Now there's a bit of a warning here, and I'll tell you what it is right now. You'd be probably saying to yourselves, this isn't very realistic, because sometimes we have these days where there's a huge move in the stock that in the context of a Gaussian distribution looks like a 2 or 3 or 4 sigma move. That's right, and because of that, when we estimate our data, we're going to discover that it indeed more or less has a Gaussian fit, but it also has kurtosis, which is fat tails, and we're going to have to make an adjustment for that. We're going to make an adjustment, for example, by adding a Poisson distribution to our Monte Carlo simulation. But as I say, an adjustment we will make. And so we acknowledge that we may have the fat tails problem right now at the outset. So practically then, what do you do in a class like Econ 136 if you have stock data that's raw, just the daily closing price, for example, as a starter, going back 1 year, 252 observations, or 2 years, a little more than 500 observations? Well, the first thing we can do is convert our raw data to continuous growth rates. And so this is shown here for Cisco over some period of time in 2017. And of course, we simply take the ratio of the logs, take the log of the ratio, or we can also take the log differences. It's the same thing. But here we're taking the log of the ratio, and we're converting this to continuous growth rates. What we're showing right there in the converted data are the actual, is the solution for the growth rate. So we solved it by taking the natural log of 22.86 over 22.34, and that comes out to 0.0230. So we convert the data to log growth data, and that is the data that we assume or hope fits a Gaussian distribution. Once we do that, then we can use statistical inference to estimate our mu. It's simply the average of the log growth rates. And to calculate our variance, it's the standard variance formula. It's each observation subtracted with the mean subtracted from it squared, divided by the sample size. And then finally, our risk proxy, standard deviation, is going to be the square root of the volatility proxy. So that's going to be very useful. Now, I said earlier, or implied earlier, that although we take raw stock prices and can convert them to log growth rates, we can also later, and get a distribution that's Gaussian, we can also later use this expression right here and convert them back to a distribution as is shown on the bottom, the transformation from the top to the bottom, where the bottom distribution turns out to be log normal. And so when we assume that our growth rates are logarithmic, as shown in the top, if we transform the distribution through this expression right there in the center, and this is using an old price for AMD as an example, then the mapping we get on the bottom, and take a look at the axes, the top has growth rate abscissa and the bottom has stock price abscissa, and the center of that is on the current price of the stock now, which I think was $3.03 in this example. Then the bottom gives us a log normal distribution that we can also work with directly to get various kinds of probability distributions. Now back to the original question, how do we represent risk? We simply say that when we compare normalized values, that the one that has the smallest standard deviation for the moment we consider less risky than the one that has the wide standard deviation. In many cases, we're going to take the standard deviations of individual stocks and divide them by the standard deviation of SPY, the S&P 500, and we'll compare those normalized standard deviations. But let's not get ahead of ourselves. That shows up in future homeworks. Now we've just covered the assumptions. Finally, if we care to visualize all of this, we can use a histogram to see if when we map this out, it looks like it's supposed to, and you'll be surprised at how often it does. One of the first things we do is apply some matplotlib in Python to map out these log growth rates to see if they're anywhere near a Gaussian distribution. And you'll see that, yeah, they sometimes have a little skew or a little lopsided, but they're not consistently skewed or lopsided. They also will pass a Kolmogorov-Smirnov test, measured up to some point. We'll talk about that in a later video or in the class. The only one thing we need to worry about a little bit is if you take a look at that distribution shown there, we do have a phenomenon of fat tails in the sense that at distributions of 3 sigma, instead of having no observations out of a sample, let us say, of 252, we have, I think, 3 on one side and 3 or 4 on the other, and that's highly improbable. That phenomenon of having fat tails, of having multiple observations out past 2 sigma, is referred to as kurtosis. Every stock distribution we have will have that, but as I've already suggested through the discussion of Poisson distributions, we have ways of dealing with that, of filtering it out and just adjusting to it. Okay, that's it for right now. This should give you a bit of a background on the pricing assumptions we make.